Okay, so today in lecture, my students were given some ice table enrichment problems to work by themselves or with a friend, and now we're going to go over them. So if you are an online student, I would recommend pausing the video, trying this problem, and then seeing if you got it right. So here's problem number 1, pause it, resume when ready. There's problem number 2, pause and then resume when ready. Here's problem number 3, hit pause and then start it back up again when you're ready. Here's problem 4. Here's problem 5. And this is number 6. Now, if you are an online student, this is also posted on the course website. There's a file called Tables Enrichment. You could just go download it from there, try it for yourself, and then check your answers as well. So now we're going to go over these problems and see if everybody got it right. Okay, now it doesn't tell me that these are solid, liquid, gas, aqueous. We're not given states of matter, so we're just going to assume that they're all states of matter that would participate in equilibrium, since I'm just using made-up substances here. So we've got, let's just pretend they're all aqueous. E plus F is in equilibrium with G plus H. And my group begins with 6 moles and 7 moles in a 1 liter vessel. So how do I convert that to molarity? Is that going to change my number in any way? It's a 1 liter vessel, right? So how do I get molarity? Because I need molarity for an ice table, right? Moles over liters. So I've got 6 moles of E, and 6 moles divided by 1 liter is 6 molar. Yes. And I've got 7 moles of F. Again, 7 moles divided by 1 liter is 7 molar. And that's all I know, right? So what does that mean that these two initially are? They're 0, right? And then the problem tells me when equilibrium is reached, we determine that 4.5 moles of G are present. Okay, so that's 4.5 moles. 4.5 moles divided by 1 liter is 4.5 molar. So that means that this went up by 4.5. What do I have to assume about H as well? It also went up by 4.5, law of conservation of mass. Where did these come from? The reactants, right? These things had to go down for these to go up, right? So what is my change going to be here? Right, subtract 4.5. And then here, same thing, right? 4.5. So this would be 1.5 and 2.5. Do we agree? Do we agree? Does everyone see where this came from? Now we want to know what's K. So K is just concentration of G times concentration of H divided by concentration of E times concentration of F. So 4.5 times 4.5, right? It's always products over reactants. 1.5, 2.5. And when I did the math, I got, when I round it to 2 sig figs, right, because I can only keep 2 significant figures, I got 5.4 as my value of K. Did you? Does that correspond to reactant favored or product favored? K is greater than 1. How do you get a number greater than 1? Is the numerator bigger or the denominator bigger? Numerator's bigger, so that means that this is product favored, right? Product favored. If you forget how to tell that, just ask yourself, how do you get a number greater than 1, right? The number on top's got to be bigger than the number on bottom. So for it to be greater than 1, that means that the products were more present than the reactants. Any questions on number 1 before we go on? Everybody good on number 1? Yes, yes, yes. Don't forget how to interpret K, okay, because that's really significant information that we need to keep fresh on our minds. We're going to be doing equilibrium until spring break, so we cannot forget how to interpret K. Okay, now we've got a second reaction that we're dealing with here. We've got SO2 plus NO2 is in equilibrium with SO3 plus NO, and K is told to be 3.75. Okay, all four gases had initial concentrations of 0.8 molar. So I, C, E. Initial concentrations of 0.8 for all four, right? So you begin by putting 0.8 molar, all of the above. Right, because it says all four. What's the value, I mean, what are the equilibrium concentrations? So what's going to happen to my reactants? They're going to go down, do we know by how much? No, we're just going to call it some variable, X. What's going to happen to my products? Going up by X. We don't know what X is yet, we're going to solve for it. So that gives me 0.800 minus X. 0.800 minus X, 0.800 plus X, and 0.800 plus X. So how do I solve for X? What do I have to use? I mean, I'm stuck unless I do something. What? I have to use my equilibrium constant, right? If I know the value of K, now I can solve for X. Because if I didn't know K, then I'm really up the creek. But I know K, right? K is equal to the concentration of SO3 times the concentration of NO divided by the concentration of SO2 times the concentration of NO2. Since I know the value of K, I can plug that in here, plug these in here, and now I can solve for X, right? So K is equal to 3.75, and so now I'm plugging these in. 0.800 plus X, 0.800 plus X, divided by 0.800 minus X, 0.800 minus X. Okay, when I have two of the exact same thing, what is that the same thing as saying? If this times this, that's the same thing as saying 0.800 plus X quantity squared, right? And this is the same thing as saying 0.800 minus X quantity squared. So I could do one of two things. I could expand this whole mess and then rearrange and then do a quadratic equation and then get an answer. That would work. What's option number 2? Because these are both being squared, I can take the square root of both sides, right? Square root of that, square root of that. So I got, let's see, what did I get? 1.936. 1.936 is equal to 0.800 plus X divided by 0.800 minus X, right? Now how am I going to get X by itself? Got to multiply both sides by 0.800 minus X quantity. That makes that go away. 0.800 minus X quantity. And now I've got to do some distribution, right? Distribute. So I got 1.549 minus 1.936x is equal to 0.800 plus x. Everyone with me how we did this so far? Just going through the algebra. All right, now let's combine like terms. Plus 1.936x makes that go away. And minus 0.800 makes that go away. All right, running out of board. So I'm left with 0.7492 is equal to 2.936x. Therefore, x equals 0.255. Congratulations to me, I solved for x. Am I done? No, what do I have to do to get the actual equilibrium concentration? Because a lot of students will stop right here and be like, well, I'm done. Right? You're not done. When are you done? You're done when you plug x back in. All right, so we take x and we plug it back into our ICE table. So 0.800 minus x, I got 0.545, right? 3 sig figs, 0.545, and then plus x, 1.06, and 1.06. And those are my final answers. Don't stop when you get x, right? Because x is great. You're 98% there, right? This is the step that a lot of students forget. They solve for x and they're like, well, I'm done, right? Got to plug x back in. Questions on number 2? Feeling good about number 2? Am I okay to erase? Okay. All right, number 3. Okay, consider this reaction. H2 plus S is in equilibrium with H2S and K 0.068. If you begin with 0.2 moles hydrogen, and this is a 1 liter vessel, right? So moles over liters, so the initial concentration is just 0.2. And 1 mole of sulfur in a 1 liter vessel. Oh, what do I need to do here? Do I need to worry about this? No, right? So that should be a sign to you. If you say to yourself, I've got 1 mole in a 1 liter vessel, how do you take the molarity of a solid? You don't, right? It's just a blob of the solid sitting there at the bottom. Is that participating in equilibrium? No. Okay, so if you forgot, if you saw that and you just kept on going, maybe the red light will stop when you see that it's a mole in a 1 liter and you can't have a molarity of a solid. That doesn't make sense. Okay. What's my initial concentration of H2S? 0. Okay. So we need to make our equilibrium table. It's asking what's the concentration of H2S. So what's going to happen to H2's concentration? Go up, down, stay the same way. It's going to go down by some quantity. We'll call it X. We don't care about the sulfur. This is going to go up by X. All right, so let's write our equilibrium expression. K is equal to concentration of H2S over the concentration of H2. All right, so that's X over 0.20 minus X. Well, now I'm in trouble unless I know the value of K, which I do know. All right, so I can take this value and plug it in. All right, so I can say to myself, okay, 0.068 is equal to X over 0.2 minus X. So how do I get that denominator to go away? Multiply both sides by it. Okay, and just like we did in the previous problem, we do some distributing. So I got 0.0136 minus 0.068x equals X, right? Can I solve this? Yes, just combine like terms, right? So I get 0.0136 is equal to 1.068x. So that means that X has a value of 0.0127. That's what I got. We're going to round to sig figs at the very end. But I'm not done when I get X, right? So plugging that in, 0.2, subtracting it, That's 0.187. We've got two sig figs we can keep. So 0.19 and 0.013. Do we agree on number 3? Questions on how we did number 3, where our numbers came from. All right. Let's go on to number 4. All right, so we're studying two isomers here. Isomers, butane and methylpropane, they are structural isomers of each other. Giving myself more room. These are both gases. So we've got butane is in equilibrium with methylpropane. These are both gases. And let's see, we've got the known value of K is 2.5. So what are we going to do here? We know the volume of the container, right? We know the number of moles of butane at least. So what's my initial concentration going to be? Is it 0.017? Please say no. Is it 0.017 as my initial concentration of butane? No. What is it? How do I get it? It's a 500 milliliter container, right? So I've got to divide by 0.5. So 0.034, right? Molarity is moles over liters. And do I know anything about this product? I'm just taking a sample of butane. Is there any methylpropane yet? No. Okay. So this is going to go down by X. This is going to go up by X. Right? So K is equal to the concentration of propane divided by the concentration of butane. We know the value of K, so that's 2.5. 2.5 is equal to X over 0.034 minus X. Right? Just like in the previous problem, we have to get X by itself, 0.034 minus X, 0.034 minus X, and then distribute. So I got 0.085 minus 2.5 X is equal to X. So when I combine like terms, I get 0.085 is equal to 3.5X. And X I got to be 0.0243, which I will round to the correct number of sig figs in just a second. Am I done when I get X though? Nope. Got to plug it back in. Plugging it in. I get myself some room here. Let's see, I got 0.0097 and 0.024. 2 sig figs. Is the temperature playing a role in my ice table? It's just extra information. Now, if I change the temperature, would I have to redo the ice table? Yes, because what would happen to K if I change the temperature? K would be different. Right, good. Questions on number 4? Questions on 4. Good. Starting to feel the pattern here. Hopefully it's a little less stressful than it was on Monday and Wednesday, I'm hoping. All right, let's do this one. You're studying a reaction between A, B, and C. You begin with 2.5 moles of A in a 5-liter flask. We don't know the value of K here. That's what we're solving for, right? We've got A in equilibrium with B plus C. We don't know what K is, right? That's what we're solving for. Is K the same thing as K EQ? Yes. Could I also write that as K C? Yes, same thing, okay? So you begin with 2.5 moles of A in a 5-liter flask. So what's my initial concentration of A? It's 2.5 moles divided by 5 liters, right? 0.50 molar. Because remember, we can only plug in concentrations here. We're not plugging in number of moles. We're only plugging in a concentration. And then B and C, initial concentrations are 0. At equilibrium, you determine that 1.33 moles of B are present. What is that going to do? Where does that show up in my ice table? At equilibrium, do I write 1.33? No, I don't. What do? It's 1.33 divided by 0.5, right? Because it's moles over liters. So that's 0.266. So what does that mean happened to C? It went up by the same amount. Okay, what does that mean happened to A? It went down. So that's 0.234. Now, do I have everything I need in order to calculate K? I do. All right, so K is equal to concentration of B times the concentration of C over the concentration of A. So that's 0.266 times 0.266 divided by 0.234. And we're keeping 2 sig figs, right? 2 sig figs. So I got 0.30. Would that be reactant favored or product favored? That'd be reactant favored, right? Questions on 5? If you missed 5 or made a mistake, you see where you made it. All right, last one. Number 6 is a little bit different than all the others. I'm going to throw that one in there and see what you did with it. Okay, for the reaction, 2NO2 is in equilibrium with N2O4. So 2NO2 is in equilibrium with N2O4. The equilibrium constant is 8.8. Analysis shows that you've got 2 times 10 to the negative third moles of NO2 and 1 times 10 to the negative third moles of N2O4 in a 10-liter flask. All right, so you've got a flask. It's got a volume of 10.0 liters. It contains 2.0 times 10 to the negative third moles NO2, and it contains 1.5 times 10 to the negative third moles N2O4. And I want to know, is that flask at equilibrium? There's only one way I can solve this problem. What do I have to do? Does anyone figure it out? There's only one answer that works here. It is not make an ice table. So if made an ice table, that's not the way to do it. Did anyone else come up with an option? Okay, what we have to do is we have to calculate Q. What is Q? What's Q called? It's called the what? The reaction. What does the Q stand for? And don't say enthalpy. That's little q. The reaction quotient. Right. And what's the difference between a Q calculation and a K calculation. K uses equilibrium concentrations. What does Q use? It uses initial concentrations, right? So Q would be concentration of N2O4 initial divided by the initial concentration of NO2 squared, right? Coefficient of 2. Do you see why we have to calculate Q? Because I've given you these conditions and I said, are you at equilibrium? There's only one way to know if I'm at equilibrium, and that's by calculating Q and comparing it to K. And I even said, if not at equilibrium, describe how it will proceed to get to equilibrium. So we got to calculate Q, which means I need to know my initial concentrations. Well, what's the initial concentration of N2O4? How do I get that?
Moles divided by
right. Moles divided by volume. Right. So problem tells me it's 1.5 times 10 to the negative third moles in a 10-liter flask. So that's 1.5 times 10 to the negative fourth molar. And I need to know the initial concentration of NO2, which is also easily attainable. Problem tells me number of moles. Problem tells me volume. So 2.0 times 10 to the negative third moles divided by 10 liters gives me 2.0 times 10 to the negative fourth molar. Now, do I have everything I need in order to calculate Q? Yes, this is my initial concentration of each substance, so I just plug them in. So that would be 1.5 times 10 to the negative fourth divided by 2 times 10 to the negative fourth squared. Why is it squared? Coefficient of 2. So when I do that arithmetic, I got 3,750. We'll worry about sig figs later, right? That would round to 3,800 if we're worrying about sig figs. But we really don't need to care about sig figs too much because all we're doing is comparing Q to K, right? Which one's bigger, Q or K? Q is much, much greater than K, right? That's a much, much greater than. So if Q is greater than K, what does that mean? Am I at equilibrium? No. When am I at equilibrium? If Q is equal to K, right, same as K. Q here is much greater than K. So which one do I have more of? Do I need, is my numerator too big or is my denominator too big? Let me rephrase the question. Which way do I need to shift? We need to shift to the left or to the, which side of this? Is that reactants or products? We're going to shift to the reactants, right? So we are not at equilibrium. We need to shift to the reactants, which, yes, is the left. Right? We need to make more products. I mean, make more reactants. Right? In other words, my denominator needs to go up. So that is the answer. And the only way that you can answer a problem like this is by calculating Q. And ICE table is not going to do it for you, right? ICE table won't do it. Any questions on this one before we end? All right, that's where we're going to stop for today. Have a nice weekend, and I'll see you Monday.